we have studied about the statement of Heisenberg's uncertainty principle, and we have concluded that it is not possible to determine the exact value of position and momentum of a very small particle like electron simultaneously. If we determine the momentum, then we cannot determine the position, that is the position becomes uncertain, and if we determine the position, then the momentum becomes uncertain. So, by this logic, Heisenberg proposed a statement where the product of uncertainty of position and the uncertainty of momentum is greater than or equal to h by 4 pi. So, from this is one statement. We can go to some other statements from this. How? We know that momentum is equal to mv. Mass is constant. So, delta P will be mass into delta V. Delta V is uncertainty of velocity. Okay. So, delta x into m delta V is greater than equal to h by 4 pi. So, delta x into delta V will be h by 4 pi m. This is the second statement. Now, we know that we can multiply and divide any equation simultaneously with the same quantity so that its value will not change. So, multiplying and dividing by delta t. So, we get multiplying and dividing by delta t to the first equation. Let us say this is equation 1 and this is equation 2 to the equation 1. Okay. So, delta p by delta t into delta x into delta t is h by 4 pi. Okay. Now, what do we know? That the rate of change of momentum is equal to force, right? This is by second law of Newton. So, we get F delta x into delta t is greater than equal to h by 4 pi, where this expression is F. Now, force into displacement, right? Change in position is displacement. So, force into displacement is delta E, that is the uncertainty of energy. So, delta E into delta T is greater than equal to h by 4 pi. So, this is the third equation. Now, from these basic equations, we can derive some other equations also. So, let's solve a question. The question is, prove that delta lambda into delta x is greater than equal to lambda squared by 4 pi. We need to prove this. How will we prove? We have the basic equation delta x into delta p is greater than equal to h by 4 pi. We have this basic equation, right? Now we know that p equal to h by lambda. We need to get the term of wavelength, right? To obtain the term of wavelength, we have this equation, the relation between momentum and wavelength. Now we can write this as h into 1 by lambda. Now we have to use derivation. So if we differentiate momentum with respect to wavelength, what we get? dp by d lambda is equal to, what is this? h into lambda to the power minus 1, right? So if we differentiate this, we get minus 1 into h into lambda to the power minus 1, that is minus h into lambda to the power minus 2. So dp d lambda equal to minus h by lambda square. So we know that in Heisenberg's equation, we take the magnitude only. We do not consider the sign. We do not consider sign, right? So for this equation also, we will not consider sign. The magnitude of delta p by delta lambda will be equal to h by lambda square. So from this equation, what do we get? If delta p by delta lambda is equal to h by lambda square, then delta p will be equal to h by lambda square into delta lambda, right? We have this equation, delta x into delta p is greater than equal to h by 4 pi. So now we will put the value of delta p in this equation. So we get delta x into delta lambda into h by lambda square is greater than equal to h by 4 pi. So delta x into delta lambda, initially we need to find this, right? Delta lambda into delta x. So delta lambda into delta x can be written as h by 4 pi into lambda square by h. So h and h is cancelled. So we get delta lambda delta x is greater than equal to lambda by 4 pi. So it is proved, right? So we have proved this statement. Now we will do another question. Prove that what is this? Delta Ek is the uncertainty in kinetic energy. So the product of the uncertainty of kinetic energy and the uncertainty in position is greater than or equal to hv by 4 pi. Now how will we prove this? Similarly, like we have done in the previous question, Ek or kinetic energy is equal to half mv square. Now if we differentiate kinetic energy in terms of velocity, what will we get? dEk by dv is equal to, we take half into m as constant into, we will differentiate v square. By differentiating v square, we get 2v, that is 2 into v to the power 2 minus 1, right. So, we get 2 and 2 is cancelled. So, we get mv. Now, dek can be written as mv into dv, or delta ek is equal to m delta v into v, right. Now, we know what is m into delta v. M into delta v can be written as delta p. So, we can say delta ek is equal to delta p into v, or delta p is equal to delta ek by v, right. Now, the main expression of Heisenberg's uncertainty principle is delta p delta x greater than equal to h by 4 pi. So, from this equation we can write delta ek by v into delta x is greater than equal to h by 4 pi. So, we can rearrange this equation to get this. Hence, this is also proved. So, we have proved this statement also. Now, we have to discuss the significance of Heisenberg's uncertainty principle. Next, we will discuss the significance of Heisenberg uncertainty principle. Right. So, the first significance is it rules out the existence of any definite path or trajectory of electrons and other similar particles. So, it rules out the existence of any definite path or trajectory of electrons and other similar particles. So, according to Heisenberg's uncertainty principle, we cannot determine the position and momentum of a very small particle like electron accurately in the same time. But to define a accurate path or trajectory, we need to know the position and momentum at the same time. So, how can we determine a definite path? When we know the exact position of the particle and the forces acting on it at the same time, then we can predict that where the particle will be and what forces will act on it after some time. So, by this prediction, we determine the path or we determine the trajectory of motion of a particle. Because for a trajectory or for a definite path, we know the exact position and exact momentum and the forces acting on the particle at every point of the definite path. But for particles like electron, which do not obey the rules of classical physics, we can see from Heisenberg's uncertainty principle that the position and momentum cannot be determined simultaneously. So, we cannot predict a definite path for such particles. So, this was also a reason for the failure of Bohr's model. The second significance was the effect of Heisenberg's uncertainty principle is significant only for motion of microscopic objects and is negligible for macroscopic objects. Why? If we see mathematically, we have seen that delta x into delta v is greater than or equal to h by 4 pi m. So, when m is very large, then the product of uncertainty, that is this term, becomes negligibly small. So, when the mass will be very large, then the products of the uncertainties will become negligibly small. So, uncertainty in such cases can be neglected. So, the third significance was the precise statements of the position and momentum of electrons have to be replaced by statements of probability that the electron has at a given position and momentum. So, the precise statements of the position and momentum of electrons have to be replaced by the statements of probability. That is, we can say the probability of the position and momentum of the electrons, but we cannot say any precise statement. So, these were the significance of Heisenberg's uncertainty principle. In the next part, we will correlate the significance of these two discoveries and we will discuss the failure of Bohr's model. Thank you.